I'm going to just, I've got, like Keely said, I've got a bit of a presentation, a PowerPoint here, and I'm going to use the PowerPoint to sort of help me showing you some of the rocks that I have. Now, most of them I've collected in Alberta myself here, and I'll attempt to tell you where I found them, so maybe you can find some of your own. And if they're not from Alberta, I'll let you know too, so you don't waste your time. Okay, so first of all, I work for the Alberta Geological Survey, and we are responsible for mapping all of the sedimentary rocks in the subsurface across the entire province of Alberta. And in doing so, we also create a bunch of what we call three-dimensional geological models that give us a picture of what the sedimentary rocks look like in the subsurface in Alberta, all the way down to the granite, the crystalline rock that forms the core of the continent of North America. And so here's a cross-section that runs from west in the mountains, east across the province into Saskatchewan. And all of these colored layers you see here are the sedimentary rocks that have accumulated in the Western Canada sedimentary basin over millions and millions of years. This records about 450 million years worth of rocks. So when we map the subsurface using oil and gas wells, each oil and gas well represents one data point, but we have many hundreds of thousands of these data points across the province. So we use those oil and gas wells to make a model of what we think these sedimentary rocks are like in the subsurface. Now, these rocks are very important to us in Alberta and to Canada because they house a lot of our oil and gas resources. They contain new resources that we're interested in, like lithium. They contain very important water, of course, water that we use for agriculture close to the surface, and there's also other deep waters in the subsurface. Another new thing is this sedimentary rock contains fluids that are hot, and eventually we'll hopefully use these hot fluids for geothermal as well. So it's really important that we understand what's going on in the subsurface. Now this is going to be awkward, but this is a 3D print of one of the geological models that we've made of the province. So if you can see it here, I'll try to hold it back. This is the surface, this is the ground surface in green and blue. This isn't water or anything, it's just a color that we use. And so this is the first layer, and this layer represents all of the Cretaceous rocks. So most of the rocks that might contain at least the dinosaurs that we have in the province. And under here are other different layers of rocks. Now this is a modeled representation of what is actually in the subsurface in Alberta. This is Mississippian rocks in age. And then we have another layer underneath that, which represents some Devonian rocks and some more Devonian rocks. We have quite a bit of Devonian rocks in the subsurface. And as I peel away these layers, you start to see older and older rocks, this blue layer here. And then the lowermost layers are Cambrian in age. And this is kind of awkward to show you, and at the very base is our craton, the granite rocks, the metamorphic and igneous rocks that form the core of our continent. And in some places that the thickness of sedimentary rocks above that is up to 5 kilometers, right next to the mountain. That's up to 5 kilometers deep by the time you get to the basement rocks, the granites. So I wanted to show you one more thing too, is another 3D print of if you were to go west into the mountains, this is kind of a representation of the faulting and folding that you see in the mountains there. So this is a 3D model that I can take apart too. And each section of these is bounded by a fault, and these are what we call thrust faults. So when we had two plates, tectonic plates coming together, they tended to push our sedimentary rock onto the craton and made a lot of these faults that we see here. And sometimes we see little parasitic folds here in the mountains. Sometimes these are exposed. And where I am in Grand Cache here, they are actually mining some coal that accumulates in some of these folds here. So that's just a 3D model of what that a section of the Rocky Mountains might look like. Okay, so just wanted to show you a couple of those models first. Let me get them out of the way, and I'll move on. I'm going to first talk about some of the fossils that I've collected in Alberta and some other fossils from outside of Alberta. And these are from Alberta's distant tropical past. I have no dinosaur bones or anything to show you, but what I do have are fossils from the Paleozoic era, so before the dinosaurs. And these are tropical fossils because they represent mostly animals that lived at a time when Alberta was very close to the equator. And if you look at this image, this black line that comes across here, that represents the equator. And if you look closely, you can see the outline of the province of Alberta here. And it was covered by a shallow ocean that flooded the Craton at the time, in this case about 375 million years ago. And in those shallow tropical oceans, just like today, these places were great places for coral reefs or reefs to form. In this case, there weren't many corals. They were dominated by things called Stromatoperoids. Now, these are a form of ancient, extinct calcified sponges, and they are really important to Alberta's history. You can see a little schematic here. They didn't look like too much. They're just kind of these bulbous, almost upside down bowl shaped forms. They took on a variety of forms actually, but they were the dominant reef formers. And if you look at this picture below, this sits outside of the offices of the Geological Survey of Canada, and it's a big chunk of a Stromatoperoid rich rock. This would have been a reef. And what's really important about this is you notice all the cavities. All of those cavities form inside of these Stromatoperoids, in this case, through a deep subsurface process where the Stromatoperoids get preferentially leached or dissolved away, and those create big pores. And importantly, those pores in the past have filled with oil and gas. And it's those types of rocks that we have explored for in the past to get that oil and gas out of. So many of our oil and gas reserves and have come from these types of reefs in the subsurface. Now, this is what a Stromatoperoid looks like. It doesn't look like a whole bunch, but it's a layered creature that had a calcite skeleton, and they would have liked areas close to the sun and some of the wave activity on these reefs, and they thrived there for many tens of millions of years. Here's another one here. This is a big chunk that I found near Fort McMurray, because the oil sands near Fort McMurray are underlain by these Stromatoperoid reefs, these Devonian Stromatoperoid reefs. And I'll talk about that a little bit more. So if you look closely, you can kind of see some of the layering of these creatures. Okay? They would have built up layer by layer. Come on. Okay, I'm going to move on, hopefully, to the next slide. Okay, here's another type of Devonian fossil that's very common throughout Alberta, both in the mountains and underneath our feet. And instead of being a calcified sponge like Stromatoperoids, these were called Faminopora, and they are a tabulate coral. So tabulate corals are very common in our modern reefs today. And this little picture you see here is a close-up representation of what those look like. Now, these were finger-like branching corals that lived in and amongst the Stromatoperoids in these Devonian reefs under our feet. Now, this one is taken from near the mountains, and so it's a rock, of course, but you see these little branching finger-like corals, and they're called Faminopora. And what's nice about some of our rocks in Alberta is that when they did turn to rocks and became fossils, that some of the details preserved really nicely. So just like in the photo you see there, you see the little galleries inside of that coral. You see those in this rock, even though it's many hundreds of millions of years old. Although they're very common from the mountains, especially around Jasper and Banff. If you keep your eye open, you can find them there. Another one was super common in the rocks around here. This particular sample I have here of Brachiopods. They look like clams, so modern day clams that you can find in and around the intertidal region, or as you're snorkeling or scuba diving in any ocean, there's always clams. These are an almost extinct creature called a brachiopod. They look very much like clams, but they're not clams. They were a different phylum. And this particular sample I have here was taken from around the Fort McMurray region, again in Devonian rocks that underlie some of the oil sands area. And this particular rock is just absolutely covered with these brachiopods. Really quite a beautiful rock. I can even flip it around and see almost the entire rock is made up of these little creatures. If you look very, very closely in here, especially with a hand lens, you can see some other critters in here, things like bryozoans and some crinoid columnals. So this is a very fossil-rich rock from the Fort McMurray region of northeastern Alberta. Now, brachiopods, again, if you keep your eyes open when you're in the mountains, especially around Jasper and Banff, you can find things like this, brachiopods, all over the place. Now, another, not a creature that lived in the water column, it's very common throughout the Paleozoic and the Mesozoic in Alberta, are a creature called ammonoids. And these are relatives of cephalopods. And today, cephalopods include things like octopus, squid, cuttlefish, and the like. And whereas octopus and squid and cuttlefish don't have an external shell, the older ammonites, their ancient relatives, had a coiled or straight shell. And this is a fossil of one such coiled shell, a simple one. And as you can see in the diagram, this creature would have been swimming like this. They were predators, probably catching other things, and it would have had its tentacles sticking out of here as it swam through the water column. Some of these were really quite large and can be almost a meter in diameter. It's what's interesting about some of the ammonoids they found in Alberta, that some of them have distinct tooth marks in them from ancient reptiles, aquatic reptiles that would have lived, like mosasaurs and the like. Oh yeah, and this one's kind of cut in half. I cut it in two to see the inside, but it's relatively simple inside, unfortunately. No nice crystals or anything. And I forget where I found that one. And another one, this is pretty common. These are relatives, ancient relatives of crustaceans and insects from a phylum called Arthropoda. And these are trilobites. Here's just one representation I found. This one actually found in British Columbia. And they were almost like the insects of the sea, and they were very common for 200 million years, a long time, from the Cambrian until they went extinct in the Earth's largest mass extinction. Not the mass extinction that caused the demise of the dinosaurs at the end of the Cretaceous. This particular extinction event happened at the end of the Permian period during the Paleozoic, and it was Earth's largest mass extinction, and this occurred 252 million years ago, whereas the one that the extinction that caused the death of the dinosaurs was only 65 million years ago. So unfortunately, these little trilobites went extinct at that mass extinction. Okay, and so this one is not from Alberta. And this is a relatively young fossil compared to what I've been showing you so far. These were the megalodon sharks, so thought to have been perhaps relatives of great white sharks. And these were incredibly large creatures. If you look at the diagram here, is a person for scale, and in the green, that's the average size of a great white shark, and the gray and red are two examples of a conservative size of a megalodon and a liberal size for a megalodon in the gray there. So they think they were up to 20 meters in length, absolutely massive. And you can see that by the size of the jaw. This woman is standing in here. There's a reconstruction of a jaw. Now, what's interesting about sharks is their bones are made of cartilage. And cartilage doesn't get preserved as a fossil very well at all. So the only thing we have left from these extinct sharks are their teeth, because their teeth are actually formed of a much formed of a much harder material. And so we can only really guess as to the size of their size, but based on their teeth, we think it was, well, in this case, up to 16 to 20 meters long. Here's a very small megalodon tooth that I purchased from a fossil vendor at the farmer's market, Strathcona Farmers Market here in Edmonton. Some of these are much, much, much bigger, like the ones you see in this reconstructed jaw that the woman is standing in here. So I think somewhat luckily for us, they went extinct 3.6 million years ago. And the teeth, I think, from what I understand, is these teeth are very common along the shorelines of South Carolina and Georgia. They kind of wash up onto the beach there, and you actually have fossil hunters that look for them there. And the next thing I want to talk about, it's super common. If you have an eye for this, these things called trace fossils are super common from many, many of the rocks that we have in Alberta. Now, trace fossils, just as the name suggests, they are fossils, but they're not the body fossils. They're not the molds of soft creatures and vertebrates or anything. They are the tracks, trails, burrows, and borings that creatures have left in and on the sediment since the dawn of complex life. And many of the rocks we have around Alberta have a variety of trace fossils. An example of a trace fossil that you might know of are dinosaur tracks. This is the record of animal activity. It's the record of dinosaur activity that doesn't include their bones. And we can get a lot of information from these trace fossils, a lot of information about the environment that the rocks formed in based on these trace fossils, because only certain critters like to live in certain places. For example, a river or a lake or a beach or a tidal channel. And so the tracks and trails and traces they leave give us a lot of information about those rocks, and we use those to help us interpret the ancient depositional environment. Now here's an example of some drawings I've made of different trace fossils, and they all have really interesting, hard to spell, hard to pronounce names. Don't ask me who comes up with them. This particular branching form of a worm that would have probed into the sediment and ingested the sediment, taking out the organic material from the sediment, is called chondrites. This interesting shaped one here is a worm-generated burrow called Tychicnus. There's a spiral-shaped one called Gyrolithes. This is something you can find on modern beaches today. This is a trace fossil called Ophiomorpha, and it's created by special types of crustaceans, which look like little shrimp or crab, and they roll up balls of sand and they armor their burrow to make it more sturdy, to make it stronger in shifting sands. Here's some traces from some shells, perhaps some brachiopods that rested on the sediment surface. These are called Lochia. And then the deep sea realm has some very interesting types of trace fossils, very complex trace fossils. This is a grazing trace called Helminthoida here, and it would have recorded a critter moving back and forth on a sediment surface, eating what organics it could find there. So those are just a very small couple examples of trace fossils. And I just wanted to show you this picture here before I show you some examples from rocks. But this is a cast, so it's a resin cast. You pour it into the surface, and that resin fills the burrows before it hardens, and then you dig that away. And this is a burrow cast I took from my master's research in New Brunswick from a lagoon. And what I wanted to show you is that there is so much animal activity beneath our feet in terms of the record of animal activity that we see in rocks. Here's a modern example of it. It's just covered with these burrows. So when you go out to the intertidal zone and say Bay of Fundy or even the west coast off of Vancouver, under your feet there are many, many animals that make their home, and these burrows that they leave behind very often are preserved in the rock record. Now I'll show you a couple here. I'll start with this one. This is an example of a trace fossil called Diplocratarian, and again I found this near Fort McMurray. It's hard to get this right. So it's a U-shaped burrow like this. As you can see the U here, and it's got these little layers like this that the creature would have stacked to the top of its burrow as it got bigger and dug deeper, and it would have lived in this burrow here. And now Diplocratarian is only found in certain marine environments, so it gives us some clues as to where that creature lived. Another one here, this is an interesting series of looping trails. I don't know if you can see that. It's called Samachnides, and these record worms that are burrowing through the sediment, in this case a siltstone, and ingesting the silt and eating the organics. And the rest of that silt is passed through its body and out the other end of the worm, and it leaves these nice trails. Now this rock is just covered with it. And if you go to a place near Exshaw, Alberta, as you go into the mountains, there's a very nice hike called Jura Creek Hike, and the rocks on all along the hike are absolutely covered with this type of trace fossil called Samachnides. It's a really neat little trace fossil. Now, another one I wanted to show you, because this is something that you can see all over the place in buildings across Canada, and especially across Western Canada from Manitoba to BC. It's a type of building stone called Tyndall limestone. And if some of you are familiar with the Royal Alberta Museum, the Royal Alberta Museum is all made of Tyndall limestone, the old one, I should say. It is all made of Tyndall limestone. And it's a really distinct looking rock. There's this light colored part here, right here. This is sort of the background limestone. And then there's this light brown colored stuff here, that's dolomite. Both are carbonate minerals, the limestone and dolomite. Now what's interesting here is this dolomite has formed all around little worm burrows. So when you look at that rock at the Royal Alberta Museum, the old one, that rock is absolutely covered with trace fossils, and they represent the little burrows of worms that lived in that carbonate mud back in the Mississippian. And if you look closely, I'm not sure if you're going to be able to see this. There's a little open burrow that you see inside of that brownish dolomite. So that's the actual burrow. And then the dolomite forms a thicker lining around that as this is buried, and you have crystal changes in the subsurface. So that next time you see that type of limestone, that really pretty limestone, it's absolutely full of fossils, but also absolutely full of trace fossils. What makes it somewhat, visually attractive is that dolomite around the burrows. Okay. So I wanted to show you a few other rocks, things that I usually like to bring to the Rock and Fossil Clinic. And there's one in particular specimen that I have that always attracts people's attention because it's got some beautiful colors, and it contains what we've called sort of finely disseminated copper in it. So when explorers and geologists are looking for copper to mine, because this is something we use on a daily basis, whether it be copper pipes here, or for electronics or many other things. This is often how they find it, is just finely disseminated. See the copper here, the brown copper in different places here. It's disseminated or mixed in with other minerals here. In this case, white quartz. The green is malachite. It's quite a beautiful mineral. It's got a very nice sort of teal green color. And then the red stuff being hematite, so an iron-bearing mineral here. So when they find this, they dig it up, and then they have to extract the copper from its host rock. So that's a cut and polished slab. So you can see the slab here. This is how it normally looks, rather dull, but if you cut it and then paint a nice clear epoxy over it, it really makes things pop. So this one's definitely in our rock cabinet at home. Now, copper is not, to my knowledge, mined in Alberta. I think this is from somewhere in the United States, and I purchased that slab because it was quite pretty. Okay, so the next one that I have is salt. We're all familiar with salt as something we use on a daily basis in our food, and it's also something that we need in moderation. And what some people don't know is that underneath our feet in Alberta, there are vast salt deposits. And this is a map I've made through my work with the Geological Survey, is the distribution of salt in Devonian rocks underneath our feet. Now you can find it all across Alberta, and these salts were deposited in these tropical oceans, but at a time when the tropical oceans continued to dry up. And when you evaporate or dry up ocean water, it has a lot of salt in it, right? Salt, the ocean tastes salty. And when you evaporate that water, you leave behind the salt. And in the case of Alberta, that happened over millions of years, and it ended up in an accumulation of salt that is in some places, like just northeast of Edmonton here in the red, where the salt deposits are over 400 meters thick. And that's been important to Alberta's history because in the 40s and 50s, we used to drill down into the salt, send fresh water down the drill stem, dissolve the salt, and then suck it back up, and then evaporate the water and use that salt that we got. It's called solution mining. And you create a little cavern underneath our feet and you use the salt. But nowadays, all these caverns that are made in the salt in the subsurface, these are used for a variety of other purposes. In some cases to store oil and gas for a time. In other cases, they're used to dispose of waters that we don't want anymore. And there are some new interesting uses for these deep subsurface salt caverns, things like compressed air energy storage, so as we hope to get a little bit greener. And so here, having said all that, here's a big chunk of salt taken from just northeast of Edmonton here in a formation called the Lotsburg Formation. And it's this beautiful, clear, pristine salt crystals that are in some cases over 200 meters thick of this salt. It's really quite pretty. And if you lick this, it tastes very salty, but I don't recommend doing that. Who knows how many people have touched this. Okay, on to another one. We know here in Alberta that we have a lot of coal deposits within our sedimentary rocks. They're mined in the mountains, they're mined in the plains, and lots of that coal is exposed, let's say at road cuts or places in the plains or the mountains. A good example is in the Red Deer River Valley, in the Badlands, there's lots of layers of coal there. And what can happen when that coal is exposed near the surface is over thousands and thousands of years, that coal may have the chance of being struck by lightning. And if that coal is struck by lightning, what happens is it starts to burn. And coal is a very efficient burning material and likes to stay lit and will continue to burn even if it goes underground. So those coal seams can burn underground and they can cook and melt the rock around it. And in this case, this rock was taken from just near Wobman where we have coal seams, and that particular coal was struck by lightning and melted this rock, and this rock was full of petrified wood and other sediments, and it formed this very light, porous rock. You see all the holes in it with the petrified wood here. It cooked that rock and made a new type of rock, is something some people call clinker, because clinker is something that forms on the inside of boilers where we burn coal to make electricity. The same sort of rock sort of starts to cling to the inside of those boilers. So it's not coal, but this rock is a consequence of burning coal underground from lightning, of all things. Now, if you go to the Red Deer River Valley, sometimes if you look at the side of the hills of the Horseshoe Canyon Formation, which make up the Badlands, you'll see some reddish tinges near layers that look kind of black. And this is where some of that coal has been lit on fire, and it's cooked the rock around it and made the rock around it a little bit red, like you see here, a little bit red. Okay. The next one I want to show you is, again, as you've noticed, I've done a lot of my work in northeast Alberta near the oil sands, but I mostly look at the old rocks that sit underneath the oil sands. And in this picture, I wanted to show you, again, this is a cross-section like the very first picture I showed you. And each one of these groups of squiggly lines represents one well where we gather information about the rocks. So this is a cross-section. And what I want to show you here is the colored units, these sedimentary units, are the Paleozoic units. These are Devonian rocks, so ancient rocks, 350 to 400 million years old. The pinks here are the salt. So we just showed you a bunch of salt from the subsurface. So here's a layer of salt. And this red line here, the squiggly red line, is what we call an unconformity. So we have Devonian rocks, 350 million years old here. And above that, we have the sands from the McMurray Formation. These are Cretaceous. Now there's a huge gap in time between the rocks that sit above that squiggly line and the rocks that sit below it. And we are missing 260 million years worth of rocks. And so we call this an unconformity. So we have young 120 million year old Cretaceous rocks in white here, and below that we have 350 million year old Devonian rocks. Now I want to show you rocks taken from a core. So this is what a core looks like as we drill down. Sometimes we take core from the underground and it comes out in tubes like this. And this core is cut in half. And these particular rocks are taken from directly above that squiggly line. So they include fragments of limestone, these beige colored pieces that were ripped up from the limestones beneath the squiggly line and incorporated into the sands, the Cretaceous sands above them. And you can see the Cretaceous sands in brown here. And the reason they are brown is because they have bitumen. So these are bitumen stained or oil sand stained sandstones that contain clasts from the Devonian rocks below. And those Devonian rocks would have been ripped up as new oceans flooded this unconformity and ripped up chunks through wave activity and river activity and so on. So this is often what geologists work with to get a picture of what's in the subsurface, are cores. And this one is taken from northeastern Alberta. Okay, next one. This one is one of my favorite and always gets a lot of attention at the TELUS Space and Science Center. For one, because it's quite large, and two, people get quite fascinated with what it represents. Now, most people are familiar with the fact that we think a very large asteroid was part of the reasons that dinosaurs went extinct 65 million years ago. There was a very large meteorite impact in the Yucatan Peninsula in the Gulf of Mexico about 65 million years ago. And in rocks younger than that impact, there are no dinosaur bones. Now, there are many such impact craters across the Earth. Many are buried within the sedimentary succession. Some are exposed at the surface. There's a really famous one called Meteorite Crater in Arizona. It's exposed right at the surface, and it's spectacular. And this particular one is taken from the Houghton Impact Crater on Devon Island in Nunavut. And now the Houghton Impact Crater is about 23 kilometers in diameter, so it's pretty big, and it's about 39 million years old. So it happened after the big one that killed the dinosaurs. Now this is what we call a shatter cone, and it's in a type of carbonate rock called a dolomite. And what happens when those dolomites are hit from a big meteorite impact, they create these really distinctive cone and cone structures called shatter cones. And you only will ever find these features associated with very large, powerful impacts on the Earth's surface.